A black hole is not a monster hiding in space. It is something stranger, a place where time bends, emptiness flickers, light loses every road home, and the universe begins to question its own rules. A dying star collapses, an invisible boundary forms, and suddenly the simplest ideas, distance, motion, temperature, even reality itself, no longer behave the way they do anywhere else. In this video, we will move slowly through that darkness, from stellar collapse and event horizons to Hawking radiation, spinning space-time, quasars, jets, and the quiet possibility of white holes and wormholes. If this kind of calm cosmic journey helps you relax, please leave a like, subscribe, and share it with someone who enjoys science at night. Thank you for spending your time here. What time is it where you're watching, and where in the world are you listening from? Leave a comment below. Now, let us begin at the edge of a collapsing star. A massive star does not become a black hole because darkness suddenly appears inside it. It becomes one because a balance that has lasted for millions of years finally fails. For most of its life, the star is held between two immense pressures. Gravity pulls every layer inward, drawing gas toward the center, while nuclear fusion in the core releases energy that presses outward as heat and light. Hydrogen is squeezed until it becomes helium, and the small difference in mass is carried away as radiance. In that long equilibrium, the star is neither escaping itself nor surrendering to itself. It is burning in a temporary truce. The larger the star, the more violently it must spend its fuel to maintain that truce, and the more fragile its future becomes. When the easy fuel begins to vanish, the core changes character. Helium can fuse into heavier elements. Carbon, neon, oxygen, and silicon may follow in successive shells, each stage shorter and more desperate than the last. The star becomes layered like an unstable furnace, with fusion continuing wherever temperature and pressure allow it. Yet this sequence does not continue forever. It approaches iron, and iron is a quiet limit. Fusing iron does not release useful energy in the same way lighter fusion does. Instead of feeding the outward pressure that has held the star open, iron gathers in the center like a growing weight. The core is no longer a source of rescue. It has become the place where support is being withdrawn. Once enough iron accumulates, the inner structure loses its ability to resist gravity. The collapse is not gentle settling. It is an inward fall of stellar material under a force that has been weighting the entire life of the star. Atomic structure is crushed. Electrons and protons are driven together. Neutrinos flood outward. The core contracts so rapidly that the surrounding layers plunge after it, and then the rebounding shock, strengthened by processes still studied in detail, tears through the star. The result is a supernova, one of the great visible releases of energy in the universe, throwing outer layers into space and scattering newly made elements into the gas that may later form other stars and planets. What remains depends on how much mass the dying star has forced into its center. If the core is not massive enough to cross the final threshold, the remnant may become a neutron star, an object with more than the mass of the sun compressed into a sphere only the size of a city. In a neutron star, matter has reached an extreme state, but not the last one. Neutron pressure and other quantum effects can still resist complete collapse. The object is unimaginably dense, yet it still has a surface, a radius, a measurable form. It remains an object in a recognizable sense, however far it lies from ordinary experience. But if the remaining core is too massive, no known pressure can hold it up. Gravity continues inward. The collapse passes beyond the range where matter can remain organized as a star, or even as a neutron star. What forms is not simply a denser ball. It is a region of space-time changed so profoundly that the usual meaning of an object begins to fail. A black hole is often pictured as a dark sphere. but that darkness is not the material body itself. It is the event horizon, the boundary beyond which light can no longer return to the outside universe. The true central structure, if general relativity is followed without correction, is called a singularity, a place where density becomes infinite and the equations stretch beyond physical interpretation. This does not mean that nature truly contains an infinitely small point in the simple way the words suggest. It means the theory has been pushed to a place where it stops giving a complete description. The singularity is less a settled object than a warning left inside the mathematics. The event horizon, by contrast, is the feature that can be defined from outside. It is not a wall. Nothing solid waits there. A falling particle would not strike a surface at the horizon itself. The boundary exists because escape paths have all tipped inward. Light, which normally sets the fastest possible route through spacetime, can no longer find any future direction that leads away. Beyond that boundary, every path that remains physically possible points deeper in. The event horizon is therefore a limit on futures. Outside it, light may still climb away, though more slowly and with more energy lost to gravity. At the horizon, escape becomes impossible. Inside it, the center is not merely a destination that matter happens to fall toward. It becomes part of the unavoidable future of anything that has crossed. This is the sense in which black holes are not ordinary objects with unusual gravity. They are regions where space-time geometry itself has been reordered. The idea did not begin as an image from a telescope. It emerged from equations, after Einstein described gravity as the curvature of space-time. Carl Schwarzschild found an exact solution for the gravitational field around a perfectly spherical mass. Hidden inside that solution was a radius where escape velocity reached the speed of light. At first, such a result seemed more like a mathematical edge case than an astronomical population. The universe was known to contain stars, gas, nebulae, and galaxies, not obvious holes in space-time. For decades, the concept remained difficult to place. It was too extreme, too clean, and too far from direct observation. Yet the same theory that made it strange also made it hard to dismiss. If enough mass were compressed within a small enough region, the event horizon followed naturally. The question became whether nature ever performed such compression. Massive stars gave one answer. The sky gave another, more patient one. Black holes cannot be seen by their own light, but they can be inferred by the way they disturb nearby matter. A dark object orbiting with a normal star can reveal itself through the motion of that companion. Gas falling toward a compact source can heat until it shines in X-rays. These clues changed the black hole from an abstract solution into a possible physical presence. One of the early and important cases was Cygnus X1, an intense X-ray source in the constellation Cygnus. The visible star in that system appeared to orbit something massive and unseen. The hidden companion was too heavy to be explained comfortably as a neutron star, and too dark to be an ordinary star. It became one of the first strong candidates for a stellar black hole, not because anyone saw a black sphere, but because the surrounding evidence had narrowed the alternatives. Since then, black holes have entered astronomy in more direct and varied ways. Stellar mass black holes have been identified in binary systems. Supermassive black holes have been found at the centers of galaxies. Gravitational waves have recorded the mergers of black holes as ripples in space-time, carrying information from collisions that released enormous energy without producing ordinary light. The Event Horizon Telescope has even resolved the shadow-like structure around supermassive black holes, including the one in the galaxy Messier 87 and the compact object at the center of the Milky Way. These images are sometimes described as photographs of black holes, but what they show is more subtle. They show glowing matter and bent light around a central darkness, a silhouette produced by the geometry near the horizon. The black hole itself remains hidden by the very rule that defines it. That distinction matters. A black hole is known less by what it displays than by what it prevents. It prevents light from returning from a certain region. It prevents ordinary matter from maintaining a stable form once collapse has gone far enough. It prevents the future inside the horizon from opening back outward. Around it, however, the universe can become intensely visible. Gas spiraling toward the horizon may form an accretion disk, heating through friction and compression until it shines across the electromagnetic spectrum. Stars near a galactic center may whip around an unseen mass in tight orbits. Space itself may carry away the signal of two horizons merging into one. The darkness is therefore not an absence of evidence. It is a boundary around evidence, shaping everything that remains outside. This is the first strange lesson of black holes. They are born from ordinary stellar physics carried to an extraordinary conclusion, from fusion, gravity, collapse, and the failure of pressure. Yet the result is not merely a dead star, it is a place where the geometry of the universe becomes the main actor, where a boundary without substance can be more decisive than any surface. And the most important thing about the object is not what it is made of, but which paths through space-time still remain possible. The collapsed star leaves behind more than a remnant. It leaves a question drawn into the structure of reality. What happens when gravity no longer acts within space-time, but begins to define the shape of space-time itself? A clock held far from a massive body does not keep time in quite the same way as a clock held closest to it. On Earth, the difference is tiny, small enough that ordinary life never notices it, yet precise instruments have to account for it. Near a black hole, that small correction becomes one of the central facts of the environment. Time is no longer a silent background against which events simply happen. It becomes part of the gravitational structure itself, stretched and redirected along with space. This is why black holes cannot be understood only as places with powerful attraction. Their gravity is not merely a force pulling things inward, as though the universe were built from invisible ropes. In general relativity, gravity is the shape of space-time, and space-time is the combined fabric of distances and durations. A falling stone, an orbiting planet, a beam of light, and a collapsing star all move through that fabric according to its curves. The stronger the concentration of mass and energy, the deeper the curvature becomes, and when the curvature grows extreme enough, the behavior of time begins to look as strange as the behavior of space. The path into this idea begins with a quieter principle. Long before black holes became serious astronomical objects, Galileo recognized that steady motion has no absolute signature. A room moving smoothly across a calm sea and a room resting on land can feel identical from the inside. A dropped object falls to the floor in either room. A person sealed away from outside reference points cannot perform a simple local experiment to prove which room is truly at rest, because rest and constant motion depend on the chosen frame of reference. Einstein took that older insight and pressed it into gravity. He considered the difference between standing on a planet and accelerating through empty space, in a closed room. A steady upward acceleration can make the floor press against the body in the same way that gravity does. Without a window, the two experiences are locally indistinguishable. This equivalence principle did not prove general relativity by itself, but it revealed the direction of the deeper theory. Gravity and acceleration were not separate in the simple way older physics had assumed. They were different ways of describing motion through space-time. The next step was to see that acceleration can arise not only from being pushed, but from being forced to follow a curved path. A body moving in a circle may keep the same speed, yet its direction is always changing. That change is a form of acceleration. Einstein's great revision was to place gravity in this geometric language. Matter and energy curve space-time, and objects moving freely through curved spacetime follow the straightest available paths within that curvature. Near Earth, those paths look like falling arcs. Around the Sun, they become planetary orbits. Near a black hole, the curvature becomes so severe that all outward paths eventually vanish inside the horizon. The familiar phrase that gravity pulls is therefore only an approximation. More precisely, space-time is arranged so that free motion bends inward. The object is not necessarily being dragged by a hand, it is following the geometry available to it. Time belongs to this geometry as completely as space does. In ordinary experience, time seems to pass at the same rate everywhere, while space offers the obvious differences. Here is a hill, there is a valley. One distance is longer than another. General relativity removes that separation. Clocks measure paths through space-time, and different paths can have different durations. A clock deeper in a gravitational field runs more slowly relative to a clock farther away. This gravitational time dilation is not a metaphor for perception or stress. It is a physical difference in elapsed time, confirmed in experiments and required in technologies that depend on precise timing. Around a black hole, the effect becomes vast because the curvature is vast. A clock hovering close to the event horizon, if it could be held there, would appear from far away to tick more and more slowly. Its light would also be stretched toward longer wavelengths, losing energy as it climbed outward. The same process that reddens light near strong gravity also tells a story about time. Each crest of the outgoing wave arrives more delayed than the last, and to a distant observer the clock seems to fade toward stillness. This does not mean time has stopped for the clock itself. Locally, if the clock remains intact and protected from other forces, it continues to mark ordinary seconds in its own frame. The difference lies between frames, between the falling or hovering object and the distant region where space-time is flatter. Relativity does not offer a single universal clock that settles the issue from above. It gives relationships between observers, each moving along a path through the same curved structure. This distinction becomes crucial at the event horizon. From far away, matter falling toward a black hole appears to slow as it approaches the boundary. The emitted light grows dimmer and redder. Signals arrive increasingly delayed. The crossing itself is never seen as a clean final moment by the distant observer, because the last light from the falling matter is stretched and weakened almost beyond recovery. Yet for the falling matter, the horizon may pass without any local announcement, especially around a very large black hole where the tidal forces at the boundary can be modest. There is no physical sign nailed to space-time. There is only a change in the global structure of possible futures. Outside the horizon, some future paths still lead away. Inside it, all future-directed paths lead deeper inward. The falling object does not watch the universe freeze. It moves through its own proper time toward whatever the interior geometry permits. The outside observer, meanwhile, thus never receives a message from beyond the crossing. The disagreement is not a contradiction. It is the same event described from paths that no longer remain mutually accessible in the ordinary way. Black holes expose this carefully because they gather several relativistic effects into one region. They slow external time measurements near the horizon. They redirect light. They bend the apparent position of background stars. They allow orbiting matter to move at enormous speeds. They make the difference between local experience and distant description impossible to ignore. A person falling freely does not feel weight in the simple Newtonian sense, because freefall removes the pressure of a supporting floor. What becomes dangerous is not gravity as uniform acceleration, but the difference in gravity from one part of the body to another. These differences are tidal forces. Near smaller black holes, they can stretch matter violently before the horizon is reached. Near supermassive black holes, the same horizon can be crossed under gentler local conditions because the curvature changes more gradually across human-sized distances. This is another strange result of scale. A larger black hole can have a more forgiving event horizon, even though its total mass is far greater. The extreme part of the journey may wait deeper inside. The time distortion also changes how energy appears. Light escaping from near the horizon spends energy climbing out of curved space-time, and its wavelength lengthens. Light falling inward gains energy as measured by local observers near the black hole. Matter descending through an accretion disk can therefore release tremendous energy before it ever reaches the horizon, not because the black hole shines from within, but because space-time outside the horizon offers a steep gravitational descent. The disk becomes a place where orbital motion, friction, magnetic fields, and relativity meet. Yet the deeper lesson remains quieter than the brightness suggests. Around a black hole, time is not an independent river flowing at the same pace for all things. It is a dimension braided into the shape made by mass and energy. The event horizon marks the place where that braid turns so sharply that the future itself points inward. This is why a black hole is both simpler and stranger than a cosmic drain. Its defining feature is not merely that escape speed exceeds light speed, though that older language remains useful. Its defining feature is that the structure of spacetime no longer contains outward escape as a possible future once the boundary has been crossed. Time near the horizon is slowed from the viewpoint of distant space, stretched into red light and delayed signals, but for the falling traveller's own clock it continues forward. The true strangeness is not that time disappears in a theatrical instant. It is that time remains local, faithful, and ordinary along each path, while the full geometry quietly removes the futures that would have led back out. The event horizon has no texture, yet it is the most decisive surface in black hole physics. It is not made of metal, plasma, ice, or light. It is not a shell placed around a hidden object. It is a boundary in causality, a dividing line between events that can still communicate with the outside universe and events that cannot. This makes it difficult to picture, because ordinary surfaces announce themselves. A planet has ground. A star has visible layers where gas becomes transparent enough for light to escape. A neutron star has an actual crust, compressed beyond ordinary matter, but still a physical exterior. The event horizon offers none of that. A particle crossing it does not collide with a wall. A clock does not stop in its own frame. A falling stone does not encounter a local sign that says the universe behind it has closed. The boundary exists because of the way all possible future paths have tilted outside the horizon. Some future-directed paths still lead outward. At the horizon, the last outward path belongs to light itself. Inside, even light has no route that increases its distance from the center in the lasting sense. The horizon is therefore less like the surface of an object and more like the point in a river where the current becomes too strong for even the fastest swimmer to make progress upstream. The swimmer still moves through local water, the body still has motion, yet the larger flow has already decided the direction of escape. This analogy fails, as all analogies do near black holes, because the river is not moving through space. Space and time themselves are arranged so that inward motion becomes the structure of the future. Still, it helps mark the essential idea. The event horizon is not a place where gravity suddenly turns on. It is the place where return has ceased to be included in the geometry. From a distance, the horizon appears to behave like a dark surface because light from within it never reaches outside observers. But the darkness is not emitted. It is the absence of all returning signals. Any object that falls near the horizon sends out light, or reflects light until the wavelengths are stretched longer and the arrival times grow farther apart. The distant observer receives a slowing, fading record. The fall seems to approach completion without ever quite delivering the final crossing. In that distant description, the object is pressed toward the edge of visibility, dimmed by gravitational redshift, and eventually lost not because it has visibly passed through a membrane, but because the information reaching outward has become too faint and too delayed to recover. The falling object, however, has a different account. Its own clock continues. If the black hole is large enough and tidal forces are not yet destructive, the horizon may pass without drama. The object does not feel the outside universe freeze in a simple picture. It may see outside light distorted, shifted, and concentrated in strange ways, but the local crossing itself is not a physical impact. This difference between distant appearance and local experience is one reason the event horizon remains so unsettling. It is real because it changes which messages can ever be exchanged. It is not locally solid because the laws of physics in a small falling laboratory can still look ordinary at the moment of crossing. General relativity permits both statements at once. The horizon is a global feature, known by the shape of spacetime across a wider region, not by a material ingredient at the boundary. This also means that seeing a black hole is never seeing the horizon alone. What telescopes detect is the behavior of matter and light outside it. Around some black holes, gas gathers into an accretion disk. The gas does not fall straight inward, because it usually carries angular momentum, a tendency to orbit that must be shed before matter can sink deeper. As it spirals, it heats, compresses, and radiates. Magnetic fields thread through the plasma. Photons curve around the central darkness. Some light that would have travelled away is bent back. Some light from the far side of the disk loops around and reaches the observer, making the region appear warped and doubled. The dark center in an image is not the event horizon itself in a simple photographic sense. It is a shadow shaped by the horizon and by the strongly curved paths of light around it. The shadow is larger than the horizon because photons passing too close are captured or redirected, leaving a dark depression against the surrounding glow. In this way, the invisible boundary becomes visible only through the failure of nearby light to escape. The photon sphere sharpens this idea. Around a non-rotating black hole, there is a narrow region outside the horizon where light can, in principle, orbit. This orbit is not stable. The smallest disturbance sends the photon either outward or inward. Yet the existence of such a path shows how severely space-time has been bent before the horizon is even reached. Light, which normally travels straight through empty space unless matter intervenes, can be guided into a circle by geometry alone. The photon sphere is not a bright ring filled with permanent light in the simple sense, because real photons rarely arrive at exactly the perfect angle and remain there forever. But it helps define this visual structure around the hole, and it helps explain why the shadow has a boundary that can be modelled. Near rotating black holes, the situation grows more complex, because spin drags space-time around with it and alters the paths of light. Even then, the central fact remains. The horizon is identified by the fate of possible signals, while the visible evidence comes from the luminous and distorted region outside. This is why black holes can be both invisible and among the most energetic systems known. The horizon contributes no ordinary light, yet the gravitational field outside it can release tremendous energy from matter that has not crossed. A black hole surrounded by no gas, no companion star, and no active disk may be almost impossible to find. It can move through space as a region of silence, known only if it bends light from background stars or disturbs nearby objects. Another black hole, fed by gas in a galactic center, can be wrapped in brilliance. The difference does not come from the horizon changing its rule. It comes from the environment around it. A bare horizon hides. A fed horizon shapes a furnace. In both cases, nothing from inside returns. The distinction is important because it prevents a common misunderstanding. Black holes do not pull everything in the universe toward them with magical reach. Far from the horizon, a black hole of a given mass attracts matter like any other object of the same mass. If the sun could be replaced by a black hole with the same mass, the planets would not instantly fall inward. They would continue along similar orbits, though life would end for lack of sunlight. The terror of a black hole is not that its gravity is infinite everywhere. It is that the mass has been compressed so tightly that an event horizon forms. The danger becomes absolute only once a path crosses the boundary, or once matter comes close enough for tidal forces, radiation, and orbital speeds to become severe. The horizon itself is the compactness made causal. It is the radius where compression has changed not only the strength of gravity, but the structure of possible escape. Inside that structure, the meaning of outward becomes unstable. In everyday space, outward is a direction. Near a black hole, directions must be understood through future paths. A rocket inside the horizon may point away from the center and fire its engines, but that firing cannot create a future that exits the hole. It can only change the manner of inward progress. Just as a person swept past a waterfall may still move within the current without restoring the upstream route. The limitation is not poor engineering. It is not merely a lack of thrust. It comes from the fact that any engine, signal, or body must still move within the light cone, the set of possible future directions allowed by relativity. At the horizon, those cones tip so far inward that the outer universe no longer lies inside them. To escape would require a path faster than light, which is not a physical path in the theory. The event horizon is therefore a promise made by geometry and kept by causality. Its strangeness is quiet. It does not need to flash, burn, or announce itself to be final. It is simply the point beyond which messages stop returning, and where the outside universe becomes unreachable, no matter how much time remains on the falling clock. The surface is invisible because there is no surface to see. Yet it is real because the universe on either side no longer shares the same future. Empty space sounds simple only because ordinary language was built far from the smaller scales. A room with no air, no dust, no heat glow, and no passing beam of light would seem to contain nothing at all. And for many purposes that description would be good enough. But modern physics does not treat emptiness as a blank absence. It treats it as the lowest available state of fields that exist everywhere. A field is not a particle, and it is not a substance in the familiar sense. It is a physical system spread across space and time, capable of taking on different values, carrying energy, and producing the particles that instruments can detect. The electron is connected with an electron field. Light is connected with the electromagnetic field. Other particles belong to their own fields, layered through the same universe without needing empty gaps between them. Even where no particle is present, the fields remain. Their quietest condition is called the vacuum. But quiet is not the same as perfectly still. This difference matters near a black hole because the event horizon is not only a boundary for falling matter, it is also a boundary laid across the fields themselves, and the fields are not easily divided into inside and outside in the way a thrown stone can be. In everyday thought, nothing means no thing. In quantum physics, the vacuum is closer to a ground state, a lowest hum beneath all definite particles. It cannot be drained into absolute zero activity because the rules of quantum mechanics do not allow every property to be fixed with unlimited precision at the same time. The uncertainty principle is often described through particles. where position and momentum cannot both be known exactly, but its deeper influence reaches fields as well. If a field were required to have a perfectly fixed value and a perfectly fixed rate of change everywhere, it would violate that quantum limit. Instead, the vacuum fluctuates. These fluctuations do not mean that large objects are appearing from nowhere in a casual way, or that conservation laws have been abandoned. They mean that at very small scales, the field does not settle into the rigid stillness that classical intuition expects. It has unavoidable uncertainty in its behavior. The old picture of empty space as a silent container becomes too simple. Space is not a stage with the actors removed. It is filled with systems whose lowest state still carries structure. One way to approach this is through light. A light wave can travel through the vacuum, yet it is still a wave. In older mechanical pictures, waves needed material media water for ocean waves, air for sound, a stretched string for vibration. Light taught physics to let go of that requirement. The electromagnetic field itself can wave. It does not need air or ether in the old sense. When light crosses interstellar space, what oscillates is not a hidden fluid, but the field, with electric and magnetic aspects changing together. Quantum theory then adds that light also comes in particles called photons, which are excitations of that field. The word excitation is useful because it avoids making the photon sound like a tiny bead moving through an empty hallway. A photon is a quantized disturbance of the electromagnetic field, a particular way the field can carry energy and momentum. Other particles can be understood with the same broad idea. Matter is not placed on top of fields. Matter is how fields show themselves when they are excited in certain ways. This view is strange, but it is not decorative speculation. It is the framework behind some of the most precise predictions in physics. Near a black hole, however, the vacuum becomes difficult to define cleanly, because the idea of a particle depends partly on the observer and on the structure of spacetime. In flat, calm spacetime, far from strong gravity, there is a natural way to distinguish a field at rest from a field containing particles. The background is stable enough that physicists can agree on what counts as empty. Curved spacetime complicates that agreement. Different observers may divide the same field into vacuum and particles differently, especially when horizons are involved. A horizon hides part of spacetime from another part. It prevents signals from one region from reaching observers in another. Since quantum fields extend across regions, a horizon changes which parts of the field can be compared and which patterns can cancel cleanly. The result is not a simple machine in which pairs of particles pop into existence at the event horizon and one falls in while the other escapes. Though that image has often been used as a rough teaching aid, the real idea is more subtle and more global. The formation of a black hole changes the field modes, the allowed patterns of field vibration across space-time. What looked like vacuum before the collapse does not have to look like vacuum afterward to observers far away. The black hole has altered the meaning of emptiness. This is where black hole physics begins to press general relativity and quantum theory against each other. General relativity describes the smooth curvature of spacetime caused by mass and energy. Quantum field theory describes particles as excitations of fields that live in spacetime. Each theory works with remarkable success in its own domain. Yet around a black hole, spacetime curvature becomes extreme, while quantum fields still have to exist and fluctuate. The horizon does not care that the field is quantum. The field does not disappear because the horizon has formed. The two descriptions must overlap, at least approximately, and in that overlap, emptiness gains consequences. The vacuum near a black hole is not merely a philosophical puzzle, it becomes tied to energy, temperature, and the long-term fate of the black hole itself. to say that nothing happens in empty space is no longer safe. The important question becomes which observer is calling it empty, over what region, and in what geometry. Vacuum fluctuations also reveal why black holes are not isolated from the quantum character of the universe, even though the event horizon blocks ordinary escape. The horizon separates causal regions, but it does not erase the fact that the fields outside must be described consistently. If part of a field pattern is hidden behind a horizon, an outside observer can no longer access the whole pattern. What remains outside may behave as though it contains a faint bath of radiation. The energy associated with that radiation cannot be free. If radiation is found at infinity, the black hole must lose mass in the bookkeeping of the entire system. This is the path that will lead toward Hawking radiation, but before that result can feel less abrupt. The vacuum itself has to be allowed to be active, not active in the ordinary sense of sparks in a dark room, but active as a mathematical and physical ground from which different observers can extract different particle content. The black hole does not need to open its horizon and let material leak out for the outside field to carry away energy. Curved space-time has changed the relationship between what was once called empty and what is later detected as radiation. The famous Casimir effect gives a gentler laboratory clue that the vacuum is not featureless. When two conducting plates are placed extremely close together, the allowed electromagnetic field fluctuations between them differ from those outside them. The result is a tiny measurable force pushing the plates together. The effect is not a black hole in miniature, and it should not be stretched beyond its purpose, but it shows that the vacuum has physical behavior. Boundaries can change field patterns. Change field patterns can create measurable consequences. Near a black hole, the boundary is not metal, it is causal geometry. The event horizon divides space-time so deeply that the quantum fields must be described with that division in mind. What emerges from the calculation is not ordinary emptiness, but a vacuum whose structure has been reshaped by collapse. This does not make black holes less dark in the classical sense. Light still cannot escape from within the horizon. A signal sent outward from the interior still fails. The rule of the event horizon remains intact. The novelty lies outside and around the hole, in the way quantum fields respond to the space-time that the black hole has made. Emptiness, under these conditions, becomes an environment with memory of curvature. The strange lesson is that the black hole does not only trap matter and light, it also forces physics to ask what matter and light are before they become definite things. It takes the most severe object in general relativity and surrounds it with the quietest state in quantum theory, then shows that the quiet state is not empty enough to remain silent forever. The next step is not to imagine something escaping from inside the forbidden region. It is to follow how the vacuum outside, once shaped by the presence and formation of the horizon, can carry a faint thermal signature away into the universe, and how that whisper can slowly change the fate of the black hole that made it possible. Hawking radiation begins with a result that seems to contradict the very definition of a black hole. If the event horizon is the boundary beyond which no signal can return, then a black hole should only gain mass or remain unchanged. Matter can fall in. Light can fall in. Even a beam aimed outward from the wrong side of the horizon has no future that leads back to distant space. In the classical picture, the black hole is therefore a one-way structure. It absorbs, curves, hides, and persists. Stephen Hawking's calculation changed that picture without breaking the horizon's rule. The radiation he described does not come from ordinary light escaping from inside. It arises because quantum fields in curved space-time do not agree with the simple idea that the vacuum remains empty for all observers. A black hole formed by collapse reshapes the field patterns outside it, and when those patterns are followed into the far future, distant observers find a faint thermal radiation. The word thermal matters because it means the radiation has a temperature, however small, and behaves like heat associated with the black hole. The object that seemed perfectly dark becomes, in quantum theory, very slightly warm. The warmth is almost impossibly weak for astrophysical black holes, yet it changes the black hole from a permanent prison into a system with a lifetime. The usual popular image says that particle pairs appear at the horizon, with one falling inward and the other escaping. As a sketch, it points toward an important truth: the black hole loses energy, while something outside carries energy away. But as an explanation, it is too local and too mechanical. The actual calculation is not about tiny sparks forming on the surface like foam. It is about quantum fields stretched across a space-time that contains a horizon. Before the black hole forms, the field may be in a state that looks like vacuum after the collapse. The existence of the horizon changes how the same field is separated into modes that distant observers call particles. Some of those modes reach far away as radiation. The horizon has not leaked in the ordinary sense. Rather, the definition of emptiness has shifted between the past before collapse and the future after the black hole is settled. The radiation is tied to the global geometry, to the way space-time has been arranged by the collapsing mass. This is why Hawking radiation can be described as coming from the region outside the horizon, or from the black hole space-time as a whole, rather than from a place inside the forbidden boundary. The distinction is not a technical decoration. It preserves the central fact that nothing climbs out from within the event horizon along a normal path. The black hole pays for the radiation through its mass. In relativity, mass and energy are not separate substances. They are exchangeable measures of the same physical content. If energy travels away to infinity as radiation, and if no other energy is supplied, the total mass associated with the black hole must decrease. At first, this decrease is extraordinarily slow. A black hole with the mass of a star would have a Hawking temperature far below the temperature of the cosmic microwave background, the faint afterglow radiation that fills the universe. In the present cosmic era, such a black hole absorbs more energy from its surroundings than it loses through Hawking radiation. It is not evaporating in any practical visible sense. It is colder than the space around it, only in a much older universe, after stars have faded and the background radiation has thinned and cooled. Would ordinary stellar and supermassive black holes begin losing mass faster than they gain it? The timescales are vast beyond biological or stellar measure. For large black holes, evaporation would take far longer than the current age of the universe, so long that the number itself is less useful than the idea it carries. Black holes are not absolutely eternal in the semi-classical theory. They are patient. As a black hole loses mass, its temperature rises. This is the reverse of familiar objects, where adding energy usually makes something hotter and removing energy makes it cooler. A smaller black hole has a smaller horizon and stronger quantum emission. The process therefore accelerates slowly at first, then more rapidly as the black hole becomes tiny. In the final stage, if Hawking's calculation remains valid all the way down, the remaining mass could be released in a sharp burst of high-energy radiation. That last moment is uncertain because it would require a theory of quantum gravity, a theory able to describe gravity itself when space-time is no longer smooth. General relativity and quantum field theory can be combined approximately outside the horizon of a large black hole, where the curvature may be strong but still manageable. Near the endpoint of evaporation, that approximation fails. The question becomes whether the black hole disappears completely, leaves a small remnant, tunnels into another kind of object, or does something no current theory can safely predict. Hawking radiation opens the door to a finite black hole lifetime, but it does not fully describe the final step through that door. The radiation also produces one of the deepest puzzles in modern physics, the black hole information problem. In ordinary quantum theory, information about the state of a system is not supposed to be destroyed. It may be scrambled, hidden in complex correlations, or practically impossible to reconstruct, but it should remain in the full physical description. A black hole seems to threaten that rule. Matter falls in carrying detailed information about its arrangement, composition, and quantum state. The radiation that Hawking first calculated appears thermal, meaning it seems to depend only on broad properties such as the black hole's mass, charge, and spin, not on the particular details of everything that formed it or fell into it later. If the black hole evaporates completely and the outgoing radiation contains no detailed record, then information appears to have vanished from the universe. This is not a small bookkeeping concern. It is a conflict between the gravitational picture, which hides information behind a horizon, and the quantum picture, which resists true loss. Many ideas have been proposed to resolve it. Some suggest that subtle correlations in the radiation carry the information out after all. Some connect the horizon with a kind of holographic encoding, where the information contained in a volume may be represented on a boundary. Some argue that the interior and exterior descriptions are related in ways that ordinary intuition cannot separate cleanly. None of these possibilities turns black holes into simple objects. Hawking radiation made them stranger by making them less final. Evidence for Hawking radiation from actual astrophysical black holes remains beyond present reach. The predicted signal from known black holes is too weak, too cold, and too easily buried beneath brighter sources of radiation. A fed black hole with an accretion disk can blaze across space, but that light comes from matter outside the horizon, not from Hawking evaporation. A quiet black hole may be classically dark and quantum mechanically glowing at a level no telescope can currently isolate. Researchers have studied analog systems in laboratories, such as fluids or condensates, where sound waves experience an effective horizon. These experiments can reproduce certain mathematical features of horizons and have reported signals resembling Hawking radiation. But they are not direct detections from gravitational black holes. They are valuable because they test parts of the underlying idea in systems that can be controlled, not because they settle the cosmic case. The real astrophysical signal may have to wait for conditions the universe has not yet provided, or for the discovery of very small black holes if such objects exist. Primordial black holes. Hypothetical objects formed in the early universe rather than from stars, would be much smaller and therefore hotter if they are real. Some could in principle radiate strongly enough to be searched for indirectly, but no confirmed population has been found. The quietness of Hawking radiation is part of its power. It does not rescue anything that has fallen into a black hole in the ordinary sense. It does not allow a message to be sent from inside the horizon. It does not make the event horizon porous like a damaged wall. Instead, it says that when quantum fields are placed on a spacetime containing a horizon, the outside universe may receive a faint thermal payment, and the black hole must lose mass in return. The escape route is not a tunnel for matter. It is a slow conversion of the black hole's gravitational presence into radiation carried away by fields. Over unimaginable stretches of time, the most inescapable object becomes capable of fading. That fading is not a defeat of the horizon, but a consequence of taking the horizon seriously in a quantum world. The boundary still forbids return from within, yet its existence changes the vacuum outside enough that darkness gains a temperature, and permanence becomes only an approximation that lasts for ages. A footprint normally comes after the foot, and ordinary cause and effect feels secure because the order is so familiar. A body presses into sand, the grains shift, and a shape remains behind. The mark has no power over the foot that made it. It records a cause without becoming one. Black holes disturb that comfort because the relationship between mass and space-time curvature is not as one-directional as everyday intuition suggests. In general relativity, mass and energy shape space-time, while space-time tells mass and energy how to move. The two sides of the relationship are not placed in a simple hierarchy. They answer each other. A star collapses because its mass can no longer support itself, and that mass curves space-time more and more severely as it falls inward. Yet after the event horizon has formed, the geometry outside the horizon becomes the way the black hole is known, measured, and, in the quantum picture, diminished. The mass is inferred from curvature. The curvature is tied to mass. The foot and the footprint begin to look less separate than they first appeared. This does not mean that ordinary objects are illusions in a careless sense, or that a black hole is only a shadow with no physical content. It means the deepest description may not begin with hard little pieces of matter sitting inside a pre-existing space. It may begin with relationships, fields, geometry, and constraints, from which the familiar idea of an object emerges only at larger scales. The phrase mass curves space-time is true, but it can quietly hide the other half of the theory. Curvature is not a decorative response drawn around matter after the real event has already happened. It is part of the gravitational field itself. A planet follows an orbit because space-time is curved, not because it is pulled by an invisible cord across an empty stage. Light bends near a galaxy because the path that counts as straight has changed. A clock runs at a different rate near a compact mass because time is included in the same geometry. In this language, the gravitational field is not a secondary stain left by mass. It is the structure within which mass, motion, and time become meaningful. When a black hole radiates through Hawking's process, the unsettling loop tightens further. The radiation is associated with quantum fields outside the event horizon, shaped by the presence and formation of the horizon. Energy travels away, so the black hole's mass must decrease. But the horizon radius and the surrounding curvature decrease with it. From one angle, the black hole loses mass and therefore curves space-time less. From another, the altered quantum state of fields in curved space-time produces radiation, and the mass changes as the cost of that radiation. Cause and description are no longer easy to arrange into the simple order of foot first, footprint second. The mathematics relates the quantities so closely that either side can feel like the handle by which the other is moved. This is not a license to turn physics into fantasy. It is a reminder that at the edge of known theory, familiar causal pictures may be only tools, not foundations. The black hole information problem deepens that reminder. Matter falling into a black hole carries detailed structure. It may be a cloud of gas, a star, a planet, or radiation, each with its own microscopic arrangement. Classical general relativity seems to hide those details behind the event horizon, leaving the outside universe with only mass, charge, and spin. Hawking radiation, at least in its simplest form, seems thermal and featureless, as though the black hole slowly returns energy without returning the detailed record of what entered. If the black hole eventually disappears, the question becomes whether the original information has truly been destroyed, or whether it was encoded in a way too subtle for the first calculation to reveal. This is where black holes make the idea of surface and volume strangely unstable. Some lines of thought suggest that the information contained in a region may be represented on a boundary surrounding it. This holographic idea does not mean the universe is a flat image in the ordinary sense. It means that the full description of what happens in a volume of space might be captured by degrees of freedom on a lower dimensional boundary. Much as the information in a three-dimensional scene can be encoded on a two-dimensional surface, black holes gave this idea force because their entropy, a measure of hidden microscopic possibilities, scales with the area of the event horizon rather than the volume inside. That fact is profoundly unlike ordinary matter. A box of gas has more room for hidden arrangements when its volume grows. A black hole's entropy follows the horizon area. The boundary appears to know something about the interior. This surface that is not a material surface becomes a ledger for what the black hole can contain. Once again, the footprint behaves less like a passive trace and more like part of the account of the foot. The event horizon marks what can be known from outside, and its area seems to measure how much hidden information the black hole can possess. This is one reason black holes have become central to attempts to unite gravity with quantum mechanics. They are not just extreme astrophysical objects. They are tests of what it means for information to be located anywhere at all. In ordinary life, information seems easy to place. A book contains words on pages. A memory belongs to a brain. A signal moves through a wire. Near a horizon, location itself becomes dependent on which observers can exchange signals and which parts of spacetime remain in causal contact. Something that falls inward may still exist in the falling description, while the outside description must account for it without ever receiving a message from beyond the horizon. The two accounts cannot simply be pasted together as though they were views from different windows in the same room. The horizon prevents that room from being whole in the ordinary communicative sense. This has led to ideas such as complementarity, where no single observer sees a violation of physical law. Even if different descriptions assign the information in different ways, to an outside observer, the information may appear to be processed at or near the horizon and eventually returned in radiation. To the falling observer, nothing special may happen at a large horizon during crossing. The tension is not easy to resolve, but it shows how black holes strain the assumption that reality must present one simple picture to every viewpoint at once. Relativity had already softened that assumption by showing that time and simultaneity depend on motion and gravity. Quantum theory softened it again by making measurement and state depend on how systems are probed. Black holes bring both softenings together in a single object, then add an event horizon as a permanent limit on comparison. Under such conditions, asking where the information really is may be less straightforward than it sounds. The deeper question behind projection is not whether everyday reality is fake. Everyday reality is stable, consistent, and richly structured at human scales. Sand holds footprints, stars shine, clocks measure time. Bodies have mass and resist acceleration. The question is whether these features are fundamental in the way they appear, or whether they arise from a deeper layer where geometry, quantum fields, and information are more tightly woven. A black hole suggests that mass may not be merely a lump of substance placed into space. It may be a way the underlying structure of space-time and fields presents itself to observers who can only access part of the full system. The horizon makes that partial access explicit. It cuts the universe into what can and cannot be communicated. It turns hidden interior states into external gravitational traits. It links area with entropy, temperature with geometry, and radiation with the slow reduction of mass. This web of relations is more delicate than the simple image of matter bending an empty fabric. The fabric has its own rules. The bending carries information. The boundary has thermodynamic meaning. The vacuum is not silent. Even the darkness has a temperature. Still, caution is essential. Black holes do not prove that the universe is a projection in the casual sense. They do not show that people, planets, or stars are unreal. They show that the categories used to describe reality may be less independent than they seem. Matter, geometry, energy, entropy. and information may be different faces of a deeper order that no completed theory has yet expressed. The black hole is where these faces are pressed into the same small region until the seams become visible. It takes the ordinary chain of cause and effect and bends it back toward itself. Mass makes curvature. Curvature shapes quantum fields. Fields produce radiation. Radiation reduces mass, and the boundary records the hidden possibilities in its area. The sequence can be spoken step by step, but the full structure feels more circular, like a quiet knot tied in the laws of nature. That knot does not undo ordinary existence. It gives ordinary existence a stranger foundation. The footprint remains in the sand, and the foot remains real enough to make it. But near a black hole, physics begins to ask whether foot and footprint are both surface signs of something deeper, something that appears as matter from one side, geometry from another, and information when the horizon refuses to let the two sides meet. A black hole seems most mysterious when it's treated as a hidden world, but one of its strangest features is how little of that world can be described from outside. After the collapse, after the horizon forms, after matter has been compressed beyond any ordinary state, the exterior universe is left with only a few measurable traits. A black hole can have mass, it can have electric charge, it can have angular momentum, which is the technical way of saying that it can spin. In the classical theory, these are the surviving public facts. Everything else that once belonged to the collapsing star appears to vanish from the external description. This star may have contained turbulent layers, magnetic storms, uneven composition, nuclear ash, rotation, sound waves, and convective motion. It may have carried the complex history of its birth cloud and the final violence of its death. Yet once it settles into a stable black hole, nearly all of that individuality is hidden behind the horizon. The outside universe does not get a catalogue of those details. It gets gravity, possible electrical influence, and rotation. This is the idea often summarized by the no-hair theorem, a phrase that makes the object sound plain, almost featureless, as though nature has shaved away every distinguishing mark. The plainness is not a weakness of the black hole. It is part of the puzzle. Ordinary astronomical bodies are rich in visible differences. A planet has mountains, weather, oceans, craters, rings, storms, and chemical surfaces. A star has temperature, color, pulsation, magnetic activity, and spectral lines that reveal its composition. Even a neutron star may carry magnetic fields, crustal behavior, and bursts that distinguish one from another. A black hole, in the ideal settled state, is more severe. If two black holes have the same mass, the same charge, and the same spin, then classical general relativity gives no external feature by which to tell them apart. Their paths may have been completely different, but their outside geometry can be the same. This compression of identity is one reason black holes feel so close to a law rather than a thing. They are not merely objects placed in space-time. They are solutions that space-time allows when mass and energy are driven into a region too compact to avoid a horizon. Mass is the easiest of the surviving traits to understand because it is the source of the black hole's gravitational reach. Far from the horizon, a black hole with a certain mass behaves gravitationally like any other body with that same mass, at least in the broad orbital sense. The difference lies in compactness. The mass is packed within a radius small enough that escape paths close around it. Astronomers can infer mass by watching nearby stars and gas respond to the invisible center, at the heart of the Milky Way. Stars orbit a compact dark object with such speed and precision that the central mass can be measured even though the object itself emits no ordinary light. In binary systems, a visible star may wobble around an unseen companion, and the orbit gives away how much mass must be present. If that mass is too large to be a neutron star and no light comes from a stellar surface, the black hole interpretation becomes strong. Mass is not hidden in the same way the interior is hidden. Its effects extend outward through curvature, shaping the motions of bodies that never cross the horizon. Charge is also allowed in principle, but in astrophysical practice it is likely to be small. A black hole can possess electric charge because charge, like mass, produces a field that reaches outside the horizon. If a charged particle falls in, its contribution to the total charge does not become unknowable from the outside. The exterior electric field changes. Yet space is filled with charged particles of both signs, and a strongly charged black hole would tend to attract opposite charge and repel similar charge, quickly neutralizing itself. For this reason, most black holes in nature are expected to be nearly neutral, though the charge solutions remain important in theory because they reveal what general relativity permits. Charge shows that the event horizon does not erase every influence of what has entered. It erases detailed access. It leaves only certain conserved quantities that can still be measured through fields outside. Spin is the most dynamic of the surviving traits. Stars rotate. Gas clouds rotate. Galaxies rotate. And collapsing matter tends to carry angular momentum with it. As a star's core contracts, rotation can intensify, just as a spinning skater turns faster when arms draw inward. A black hole formed from rotating matter is therefore expected to spin, and many black holes appear to do so rapidly. Spin changes the space-time around the hole in a way that mass alone does not. A non-rotating black hole can be pictured, in the simplest model, as having a spherical symmetry. A rotating black hole is more complex. It drags nearby space-time around with it, creating an environment where the geometry itself has a direction of circulation. This effect is called frame dragging. It is not a mere metaphor for whirlpool motion in a fluid, because there is no water and no material vortex. It is twisting of reference frames, a statement that near the rotating mass, the definition of standing still relative to distant space becomes impossible in certain regions. Spin gives the black hole an exterior structure that remains consistent with the no-hair idea, but is far from dull. The mathematical description of a rotating black hole is known as the Kerr solution, and it introduces several important surfaces outside and near the horizon. The outer event horizon still marks the boundary from which no future directed signal can escape to distant space. Outside that, for a rotating black hole, lies the ergosphere, a region where space-time is dragged so strongly that no object can remain at rest with respect to the faraway universe. Anything in the ergosphere must share the rotation in some degree. This does not mean it has already fallen beyond recovery, because the ergosphere extends outside the event horizon. Escape is still possible there, but stillness is not. The black hole's spin has imposed motion on the local geometry. From a small list of properties comes a region where energy extraction becomes possible, where light paths twist, and where matter can be driven into some of the most powerful behavior observed in galaxies. The simplicity of black holes is therefore deceptive. Mass, charge, and spin sound like sparse ingredients, but they reshape space-time in ways that have many consequences. Mass determines the scale of the horizon. Spin changes the shape of the surrounding geometry and can alter the innermost stable orbits available to matter. Charge, even if usually small in nature, demonstrates how fields can carry conserved information outward. Together they define the external black hole in classical physics. The theorem does not say that nothing interesting happens near black holes. It says that the black hole itself, once settled, does not preserve ordinary surface features for the outside world. The richness has moved from the object's material individuality into the geometry and environment. A black hole with an accretion disk may look alive with heat, light, magnetic turbulence, and jets, but those features belong to matter outside the horizon. The hole at the center remains governed by a compact set of parameters. This distinction becomes especially important when considering information. If every collapsed star becomes externally describable by only mass, charge, and spin, then where did the other details go? Classical relativity answers in a cold way. They went behind the horizon, no longer able to influence the outside except through the allowed conserved quantities. Quantum theory is less willing to leave them there forever, especially if Hawking radiation eventually shrinks the black hole. The no-hair idea therefore supports both the elegance and the unease of black hole physics. It makes black holes mathematically manageable, reducing their exterior identity to a few numbers. It also sharpens the question of whether nature truly permits so much detailed information to disappear from accessible reality. The cleaner the exterior becomes, the harder the hidden accounting problem feels. The observational side reflects this balance. When astronomers estimate a black hole's mass, they track orbits, velocities, radiation from disks, or gravitational waves from mergers. When they estimate spin, they study the behavior of matter close to the horizon, the shape of X-ray emission, or the imprint of rotating spacetime on the merger signal. Charge is usually assumed to be negligible unless evidence suggests otherwise. The black hole is measured through effects, not surfaces. Its traits are read from the motion of stars, the heat of gas, the timing of waves, and the geometry of light. The central object withholds almost everything, yet the surroundings speak in disciplined patterns. The no-hair theorem is not the end of the mystery. It is the narrowing of it. A black hole may erase mountains, chemistry, and stellar memory from its external face, but it does not erase influence. It leaves behind a mass that curves time, a possible charge that reaches through fields, and a spin that twists the very frames by which motion is judged. Out of those few surviving facts comes a universe of effects, and the next one begins where rotation stops being a quiet property and becomes a forceful rearrangement of space-time itself. A rotating black hole does not merely sit inside space, it changes what space means nearby. Around a non-rotating black hole, the geometry can be severe, but it has a kind of stillness in its symmetry. Paths curve inward, clocks slow relative to distant observers, and the event horizon marks the place where outward futures vanish. Add spin, and the situation gains a new kind of motion. The black hole is not rotating through space-time like a ball spinning in a room. Its rotation is written into the surrounding geometry, dragging local frames along with it. This effect is called frame dragging, and in weak form it occurs around any rotating mass, including Earth. Around a black hole, especially one spinning rapidly, it becomes a defining feature of the environment. The closer a body comes, the harder it becomes to define rest in the old distant sense. The space-time around the hole has acquired circulation. It is not a whirlpool of matter, though matter may later trace it. It is a whirlpool of reference, a region where the rules for saying that something is standing still begin to turn with the black hole itself. The strongest expression of this outside the horizon is the ergosphere. The ergosphere surrounds a rotating black hole and reaches beyond the event horizon, forming a zone where escape can still be possible, but remaining motionless with respect to distant stars cannot be. An object then must rotate in the same general direction as the black hole, not because a surface has grabbed it, but because space-time has been dragged around so strongly that every allowed local frame is carried along. This is a difficult idea because it sounds like space has become a substance. General relativity does not require space to be a material fluid, yet it does allow geometry to have behavior. In the ergosphere, the geometry says that the future paths available to particles and light all share part of the hole's rotation outside the ergosphere. A rocket could in principle hover in place relative to the distant universe if it had enough thrust. Inside the ergosphere, that kind of hovering is no longer one of the available physical states. The object can still climb away if it follows the right path and has enough energy, but it cannot refuse the turn. This gives the ergosphere a different character from the event horizon. The horizon is a boundary of no return. The ergosphere is a boundary of no stillness. Between them lies one of the most unusual energy reservoirs in known physics. Rotation contains energy, and a spinning black hole stores an enormous amount of it in the structure of its spacetime. The black hole is not simply massive, it has angular momentum, and angular momentum can be exchanged. Roger Penrose realized that the ergosphere might allow a process by which some of that rotational energy could be extracted. In the simplest version, an object enters the ergosphere and splits into two pieces. One piece falls into the black hole along a path that, from the viewpoint of distant observers, carries negative energy relative to infinity. The other piece escapes outward with more energy than the original object had when it entered. The extra energy has not been created from nothing. It has been taken from the spin of the black hole. After the process, the black hole rotates very slightly more slowly. The gain outside is paid for by a loss in the hole's angular momentum. This Penrose process sounds almost impossible, because negative energy is not part of ordinary intuition. Yet inside the ergosphere, the dragging of space-time changes how energy is defined relative to faraway observers. Energy, in relativity, is not always a simple local substance that looks the same from every frame. It depends on symmetries and reference frames, and the ergosphere permits paths that are strange by distant standards while remaining allowed in the local geometry. The falling fragment does not carry a magical negative mass in its own experience. It follows a possible path in a region where the black hole's rotation has altered the bookkeeping. The escaping fragment leaves with a surplus because the total accounting includes the black hole itself. The process is elegant because it makes the black hole less like a passive trap and more like a rotating gravitational flywheel. In principle, energy can be drawn from the twist, though doing so with ordinary machinery would demand conditions far beyond present technology. The useful lesson is not that spacecraft can soon graze black holes for power. It is that space-time geometry can store and surrender energy in ways that have no everyday counterpart. A related mechanism appears in astrophysics through magnetic fields and plasma rather than engineered fragments. Around many spinning black holes, charged particles in accretion disks generate strong magnetic fields. Those fields can thread the rotating region near the hole and extract energy from its spin, helping power jets that leave the system at relativistic speeds. This is often discussed through the Blandford-Znaiec process, a more realistic candidate for how rotating supermassive black holes help drive enormous outflows. The details are complex because the region is filled with hot plasma, turbulence, radiation, and magnetic structure. Still, the underlying theme is similar. The spin of the black hole is not locked away behind the horizon in a completely useless form. Through the exterior geometry and surrounding fields, some of its rotational energy can influence matter outside. The darkness at the center can help power the brightest engines in galaxies, not by emitting light from within, but by twisting the environment in which gas and fields move. Frame dragging also complicates the idea of faster-than-light motion. Nothing locally outruns light. That rule remains intact. A particle in the ergosphere still has a local light cone, and it still must move within the allowed future direction set by relativity. yet the frames themselves are being dragged, and from far away the region can look as though motion has acquired an extra component from spacetime. This distinction matters. The black hole is not allowing matter to break the speed limit in its own neighborhood. It is changing the neighborhood. The speed of light remains the local limit, but the reference frame in which local speeds are measured is no longer aligned with the calm frame of distant space. In the strongest dragging, near the horizon, resisting the rotation would require an impossible path. The object does not choose to move around the black hole in the usual sense. Rotation has become built into the future directions available there. Such behavior hints at why some speculative ideas for rapid travel focus not on pushing a craft through space faster than light, but on changing the geometry around it. The comparison must be handled carefully. A black hole's frame dragging is a natural consequence of immense mass compressed within a horizon and set into rotation. It does not provide an engineering blueprint for human travel. The energies involved are extraordinary, and the surrounding environment is often lethal, filled with intense radiation, tidal gravity, and plasma heated to extreme temperatures. But black holes show that relativity's speed limit is more subtle than a simple rule painted across an unmoving stage. Objects cannot locally exceed light speed, yet space-time itself can have global arrangements that make distant comparison surprising. The expanding universe already gives another version of this subtlety, as distant galaxies can recede faster than light because space between regions expands. A rotating black hole gives a more compact and violent version, where space-time is not expanding but being dragged. In both cases, the deeper point is that relativity limits motion through local space-time, while the geometry of space-time remains capable of behavior that ordinary language strains to express. The ergosphere is therefore not a decorative feature added to the black hole. It is the region where spin becomes physically unavoidable outside the horizon. It shows that the three public traits of a black hole are enough to shape a complicated surrounding world. Mass gives the horizon its scale. Spin twists the possible frames. The interaction between rotation, accreting matter, and magnetic fields can turn a dark, compact object into the anchor of a vast energetic system. Even before matter crosses the point of no return, it may be swept through a geometry where standing still is forbidden, where energy can be borrowed from rotation, and where the difference between motion and the motion of the frame itself grows thin. This is the calm strangeness of rotating space-time. The black hole does not need a surface to pull on the universe around it. Its spin is enough to turn the meaning of rest. And in that turning, the next stage of the story begins matter trying to fall inward, while its own angular momentum refuses to let the descent be simple. Matter falling toward a black hole is rarely falling straight. The simplest picture imagines gravity as a downward slide, with gas, dust, stars, and light all drawn into a central darkness along clean radial paths. But real matter usually arrives with sideways motion. It may come from a companion star, a disrupted cloud, or the crowded center of a galaxy, and almost nothing in space begins with perfect aim. A small sideways drift becomes important as the object descends, because angular momentum is conserved. The closer matter moves toward the black hole, the smaller its orbit becomes, and the faster it must circle to preserve that motion. The effect is familiar in gentle form when a spinning skater draws arms inward and turns more quickly, but near a black hole the same principle is carried toward an extreme. Gas that might have seemed destined for direct capture is forced into a spiral. The black hole pulls inward, yet momentum insists on sideways motion. Between those demands, matter gathers into an accretion disk, a flattened, rotating structure where the journey into darkness can be delayed for immense lengths of time. This is the accretion barrier. It is not a solid obstacle, and it is not a refusal by gravity. It is the consequence of motion that cannot simply vanish. To fall through the horizon, matter must lose enough angular momentum to move inward. Until it does, it circles, shears, heats, and waits in a violent kind of suspension. The disk forms because different parts of the incoming gas collide and settle into a common plane. Random motions cancel more easily than rotation does. Gas moving upward may strike gas moving downward. Streams cross, shock, and radiate energy away. Over time, the material flattens into a broad orbiting flow, because rotation remains as the durable remnant of the original motion. Once the disk exists, its inner regions orbit faster than its outer regions. This difference in speed creates shear, and shear allows friction, turbulence, and magnetic effects to move angular momentum outward. The inner gas gives some of its sideways motion to gas farther out, and with that loss it can slip inward. The outer gas receives angular momentum and may drift away or spread. The process is not smooth like water draining through a hole. It is more like a crowded exchange, with energy and momentum constantly redistributed. Without such transport, the disk would stall. Matter would keep orbiting rather than falling. Black holes can be excellent traps, but only for material that has found a way to shed the motion that keeps missing the target. This is why accretion can take so long. In some systems, gas may orbit for years, centuries, or far longer before reaching the inner regions. Around supermassive black holes, the full feeding structure can extend across distances comparable to a solar system or larger, while the horizon itself remains only the final boundary at the center. The disk is not a decorative ring around a black sphere. It is the visible record of a problem being solved slowly, how matter gives up enough angular momentum to cross a horizon. The closer the gas comes, the more severe the environment becomes. Orbital speeds can approach a significant fraction of the speed of light. Collisions become energetic, compression grows intense, magnetic fields become twisted and amplified through the motion of electrically charged plasma. The gas heats to millions of Kelvin, becoming a plasma in which electrons and atomic nuclei move freely. At those temperatures, the disk shines strongly in ultraviolet light and X-rays. The black hole itself emits no ordinary light from within the horizon, but the matter struggling to reach it can become one of the brightest sources in the universe. This brightness is not a contradiction of darkness. It is the cost of the descent. Gravitational energy is being converted into heat and radiation before the material disappears from view. The efficiency can be far greater than ordinary nuclear burning in stars. Fusion in a star converts a small fraction of mass into energy. Accretion onto a compact black hole can release a much larger fraction of the infalling matter's rest energy, especially when spin allows the innermost stable orbit to lie closer to the horizon. The disk is therefore not merely a waiting room. It is an engine powered by gravity, rotation, and the difficulty of falling cleanly. There is also an innermost stable circular orbit, a final zone where steady circular paths stop being possible. Outside this region, matter can continue to orbit if it keeps the right speed and angular momentum. Inside it, stable orbit gives way to plunge. The exact location depends on whether the black hole spins and whether the matter orbits with or against that spin. For a rapidly rotating black hole, matter moving in the same direction can orbit closer before the final fall. This means it can release more energy before crossing the horizon. The disk's brightness and spectrum therefore carry clues about the black hole's spin, even though the horizon itself remains dark. Astronomers read those clues in broadened emission lines, flickering X-rays, and the timing of light from the innermost flow. The details are hard to separate from turbulence, magnetic fields, and the geometry of the disk, but the principle is clear. Matter outside the horizon is forced to reveal information about the spacetime it is trying to enter. The accretion barrier is also the reason falling into a black hole is not simply a matter of being close. A star can pass near a black hole and survive if its path carries enough speed and distance. A cloud can be stretched, disrupted, and only partly consumed. Some matter may be flung outward, some may join the disk. Some may eventually cross the horizon after losing momentum through interaction with the rest. Even when a black hole tears a star apart, the debris does not always vanish at once. It streams around the black hole, collides with itself, circularizes, and produces a flare as part of the material becomes an accretion flow. The event horizon may be absolute, but reaching it is a dynamical process. Gravity invites the fall. Angular momentum delays it. Radiation announces the delay. Magnetic fields complicate it further. In hot disks, charged particles do not move independently through empty space. They are tied to fields that can store and move energy. Turbulence can arise when magnetic fields connect neighboring rings of gas, allowing inner and outer regions to exchange angular momentum. This magnetized turbulence is thought to be central to how disks feed black holes at all. The disk has to find an internal language for moving momentum outward while letting mass move inward. Without that language, the black hole would be surrounded by orbiting matter that could not complete the last part of the journey. With it, the disk becomes unstable, luminous, and productive. Its light may flicker as clumps form, heat rises, and magnetic structures rearrange. Around stellar mass black holes in binary systems, this can produce changing X-ray states, where the disk brightens, fades, hardens, or softens depending on how material is supplied. Around supermassive black holes, the same broad physics is stretched to galactic scales, producing active nuclei whose output can influence star formation across their host galaxies. The barrier therefore shapes not only the fate of falling gas, but also the environment far beyond the hole. Energy released in the disk can heat surrounding clouds, push winds outward, and regulate how much material continues to feed the center. A black hole can grow by accretion. Yet accretion can also resist growth by producing radiation and outflows that disturb the supply. The system becomes self-limiting in some conditions. Feeding creates light. Light pushes back. In the centers of galaxies, this feedback may help explain why the growth of supermassive black holes is connected with the evolution of their host galaxies. The black hole is tiny compared with the galaxy, but the energy released near the horizon can reach much farther than the horizon itself. Once again, the important action occurs outside the point of no return. The darkness defines the limit, but the spiral toward it shapes the visible universe. The accretion barrier gives black holes a slower and more intricate character than the simple image of a cosmic drain. They do not swallow everything instantly. They wait behind rules of motion. Matter must negotiate with its own angular momentum, with the disk around it, with magnetic fields, with radiation, and with the changing geometry near the innermost orbit. Some material finally crosses, some is delayed, some is thrown outward, some shines so intensely before disappearing that it can be detected across cosmic distances. The black hole remains silent at the center, but the failed simplicity of the fall becomes radiant. What looks from far away like a dark mouth is often surrounded by a long argument between gravity and motion, and that argument prepares the next phenomenon, the narrow, powerful jets that send part of the surrounding system not inward, but outward across intergalactic space. Jets begin where the inward story becomes incomplete. Around some black holes, matter spirals through a hot accretion disk, losing angular momentum and releasing energy as it moves toward the horizon. That alone would be extreme enough. Yet in certain systems, a portion of the surrounding plasma does not complete the descent. Instead, it is organized into two narrow streams and launched away from the central region at speeds close to that of light. These are relativistic jets, and they can stretch far beyond the galaxy that produced them. They appear as long, focused beams of radiation and particles, sometimes piercing intergalactic space for distances so large that the black hole itself becomes almost impossible to imagine at the same scale. The central horizon may fit within a region smaller than the planetary orbits around a star, while the jet can extend across hundreds of thousands or even millions of light years. The contrast is one of the most striking in astrophysics. A boundary that emits no light can anchor a structure visible across the universe. The first caution is that the jet does not come from inside the black hole. Nothing that has crossed the event horizon returns to become part of an ordinary outflow. The material in the jet is drawn from the environment outside the horizon, especially from the accretion disk and from the magnetized plasma around the rotating black hole. This distinction preserves the rule that defines the black hole while still allowing the system to appear eruptive. The surrounding space-time, disk, and magnetic fields are arranging some infalling material into an escape route before the point of no return is crossed. That escape is not gentle. The plasma is heated, ionized, threaded by magnetic fields, and accelerated into narrow channels above and below the disk. To understand why those channels form, the disk has to be seen not as a simple ring of gas, but as a moving electrical environment. Plasma contains charged particles. Charged particles in motion generate magnetic fields. As the disk rotates, those fields can twist, strengthen, and connect different regions of the flow. Near a spinning black hole, the geometry itself may also help wind the magnetic field lines, because frame-dragging forces local reference frames to turn. The result can be a kind of cosmic magnetic machinery, where rotation is converted to directed motion. In many models, magnetic fields act like rails or funnels. They do not need to be solid to guide particles. Charged particles spiral around field lines, and if the field structure is strong and ordered enough, it can collimate the outflow, squeezing what might have been a broad wind into a narrow beam. Some energy may come from the accretion disk, some may come from the rotational energy of the black hole, extracted through the magnetic field in the region outside the horizon. The exact balance differs from system to system and remains an active subject of research, but the essential point is clear. Jets are consequences of rotation, magnetism, plasma, and curved space-time meeting under extreme conditions. Once launched, the jet carries energy with extraordinary focus. The particles inside may move at relativistic speeds, meaning their motion must be described using relativity rather than ordinary mechanics. At such speeds, radiation becomes strongly beamed in the direction of motion. A jet aimed close to Earth can appear far brighter than an identical jet aimed sideways or away, because its light is concentrated toward the observer. This effect helps explain why some active galactic nuclei seem so intensely luminous and variable. The object is not necessarily producing equal brightness in all directions. It may be sending a narrow beam across space, like a lighthouse whose sweep is controlled by cosmic geometry rather than a rotating lamp. When the beam points near the line of sight, the source can seem amplified. When it points elsewhere, much of its power is missed. This directional nature makes black hole systems difficult to interpret. Quasars are among the most powerful examples of black hole feeding. A quasar is an extremely luminous active galactic nucleus, powered by matter accreting onto a supermassive black hole. The black hole itself remains dark, but the inner disk and surrounding region can outshine the combined stars of the host galaxy. In the early universe, When gas was more abundant and galaxies were younger, quasars were more common. Their light has crossed billions of years to reach telescopes, carrying evidence of black holes that were already massive when the cosmos was still young. The name comes from their early appearance as star-like radio sources, but the reality is far larger. A quasar is not a star. It is a galactic center in a brief and powerful feeding state, where gravity converts infalling mass into radiation with remarkable efficiency. Some quasars also produce jets, and when they do, the system becomes visible not only as a blazing center, but as a structure that can disturb its surroundings on galactic and intergalactic scales. The brightness of a quasar can make its host galaxy difficult to see. The central engine may overwhelm the starlight around it, reducing a vast galaxy to a faint background behind a point of brilliance. To study the galaxy, astronomers must separate the central glare from the older, softer light of billions of stars. To study the black hole, they must infer mass, spin, feeding rate, and orientation from radiation produced outside the horizon. The quasar becomes both a beacon and a veil. Matter near a black hole can release energy far more efficiently than ordinary stellar fusion. The gravitational descent is steep, and the last stable orbits near the hole allow gas to shed a large fraction of its energy before disappearing. This is why a region smaller than a solar system can rival or exceed the output of a galaxy. Jets add another layer by carrying energy away mechanically, not only as light but as moving plasma and magnetic structure. When a relativistic jet strikes surrounding gas, it can inflate enormous lobes, heat the intergalactic medium, and carve cavities in the hot atmosphere of galaxy clusters. These effects mean that black holes can influence regions vastly larger than themselves. A supermassive black hole at a galactic center may be tiny compared with the galaxy, but the energy released during active phases can regulate the supply of gas from which new stars form. If the jet or radiation heats gas enough, it may prevent that gas from cooling and collapsing into stars. If it compresses clouds in other places, it may help trigger star formation locally. The outcome depends on environment, timing, and scale. Black holes are therefore not only endpoints of collapse. In active galaxies, they participate in the evolution of their hosts. Their feeding can shape the future of surrounding gas, and their jets can draw lines of influence across space long after the original matter avoided the horizon. There is a quiet paradox in this. The black hole is defined by inescapability, yet some of the most visible signs around it are signs of escape. The escape is not from inside, and it does not violate relativity. It is a pre-horizon escape, an outward channel carved by magnetized rotation from material that might otherwise have joined the inward flow. The system divides the supply. Some matter loses angular momentum and falls, some transfers energy outward, some becomes radiation, some is lifted into jets and sent away at nearly light speed. A black hole surrounded by a disk is therefore not a simple mouth. It is a sorting region where gravity, motion, and magnetism decide many fates before the horizon takes the final share. This also explains why not every black hole has visible jets. A quiet black hole without much nearby gas may produce no bright disk and no obvious outflow. A feeding black hole with weak or tangled magnetic structure may shine without launching a strong jet. A rapidly spinning black hole in the right environment may drive beams powerful enough to be seen across cosmic history. The horizon remains governed by the same rule in all cases, but the environment around it determines whether the universe sees silence, X-ray flickering, quasar brilliance, or vast radio lobes spread beyond the host galaxy. The jet is the black hole system's most extended gesture, a sign that the consequences of collapse do not end at the boundary where light fails to return. They move outward through fields, particles, radiation, and surrounding gas. Darkness remains at the center, but its neighborhood can become luminous enough to right across the sky. Jets and quasars show that the physics of the horizon cannot be separated from the physics of everything just outside it. The black hole hides its interior perfectly, yet it can make the nearby universe violently expressive. It can remain unseen while shaping beams longer than galaxies. It can consume matter while helping to expel matter. It can be the darkest feature in a system that becomes one of the brightest objects in the cosmos. The next question follows naturally from that scale. If black holes can power quasars visible across billions of years, then some of the most distant lights in the sky are also messages from the early growth of immense horizons. And those messages reveal a puzzle. Some black holes appear to have become enormous before the young universe seems ready to have built them. Some of the largest black holes are found not by looking nearby, but by looking far away, where distance turns into history. Light that has crossed billions of years reaches telescopes as a delayed record, showing galaxies as they were when the universe was younger. In those distant records, astronomers find quasars powered by supermassive black holes already weighing millions, billions, and in some cases tens of billions of solar masses. The surprise is not that such objects exist now. Given enough time, a black hole at the center of a galaxy can grow by feeding on gas, swallowing stars, and merging with other black holes during galactic collisions. The surprise is that some of them seem to have grown so large so early. The young universe was dense, turbulent, and rich in gas, but it was also young. Time itself becomes the constraint. A black hole cannot become enormous merely because gravity wants it to. It needs a starting seed, a supply of matter, and a way for that matter to lose angular momentum and radiate energy before crossing the horizon. Growth is not instantaneous, and the brightest distant quasars press against the question of whether ordinary pathways are fast enough. The Milky Way offers a calmer comparison. At its center lies Sagittarius, a star, a supermassive black hole of about 4 million solar masses. It is massive by any human standard, yet modest by the standards of the most powerful quasars. The stars around it reveal its presence through tight orbits, moving around an invisible compact mass in the galactic center. Today it is relatively quiet, feeding weakly compared with an active quasar. Its darkness doesn't mean it lacks gravity. Only that little material is currently falling in with enough intensity to produce a brilliant disk. Nearby galaxies host larger central black holes, including Messier 87, where the Event Horizon Telescope resolved the glowing structure around its shadow. Yet even that enormous object sits in the present universe as a mature remnant of long galactic history. The distant quasars create a different feeling. They're seen when cosmic structure was still assembling, and some appear to contain black holes that had already reached masses far beyond what simple stellar collapse followed by steady feeding can easily explain. To build such a giant, the universe must begin with a seed. One possibility is that the first generations of massive stars collapsed into black holes. These early stars may have been far more massive than typical stars today because the primordial gas contained almost no heavy elements, making it harder to cool and fragment into smaller clumps. Their remnants could have provided the first stellar mass seeds, but a seed of tens or hundreds of solar masses still has a long way to grow before it becomes a billion solar mass quasar engine. Growth through accretion faces a natural limit. As gas falls in, it shines. That radiation pushes outward on the incoming material. If the luminosity becomes too high, radiation pressure can fight the inflow and restrict the feeding rate. This balance is known as the Eddington limit. It does not make rapid growth impossible, but it makes uninterrupted rapid growth demanding. The black hole would need a sustained fuel supply, and favourable conditions over hundreds of millions of years, without too many interruptions from feedback that heats or expels the gas around it. Another possibility is that some early black holes began much larger, in dense primordial gas clouds. Under special conditions, a cloud might collapse directly into a black hole rather than first forming ordinary stars. Such direct collapse seeds could begin with thousands or even hundreds of thousands of solar masses, shortening the path to quasar scale. This idea gives early giants a head start, but it also requires particular environments. The gas must avoid fragmenting into many smaller stars. Cooling, turbulence, radiation from nearby young galaxies, and chemical enrichment all matter. The conditions cannot be assumed everywhere. They may have been rare, which would fit the rarity of the brightest early quasars, but the details remain under study. A third contribution comes from mergers. Small galaxies merge into larger ones, and their central black holes can eventually sink together and combine. In the crowded early universe, mergers were common. They could help build mass, especially when paired with heavy gas feeding. But black holes need time to find one another after their host galaxies collide. Surrounding stars, gas dynamics, and gravitational wave emission all influence whether the final merger happens efficiently. Growth likely did not come from one channel alone. It may have required several processes working together unusually large seeds, dense gas inflows, periods of super Eddington feeding, and repeated mergers inside the first large galaxies. Observational bias complicates the picture. The black holes most easily found at great distances are not ordinary quiet ones. They are quasars, because quasars are bright enough to be seen across cosmic time. This creates a selection effect. The distant universe may appear filled with extreme black holes because only the extreme active systems rise above the limits of detection. A massive black hole that is not feeding brightly may remain hidden inside its host galaxy. A smaller black hole feeding at a high rate may outshine a larger quiet one. Brightness, orientation, dust, and jet beaming can all distort the census. This does not remove the early growth problem, because confirmed high redshift quasars really do imply large central masses, but it changes the surrounding interpretation. The known sample is not a fair inventory of all young black holes. It is shaped by what current instruments can see: the luminous, the active, the favourably oriented, and the rare. The early universe also gave black holes advantages that the modern universe often lacks. Gas was more abundant, galaxies were more compact, collisions and instabilities were more frequent. Large streams of cold gas may have flowed along cosmic filaments into young galaxies, feeding their centers more efficiently than quiet mature galaxies can today. In a present-day spiral galaxy, much gas has already been turned into stars or heated and redistributed. In elliptical galaxies, star formation may have largely shut down after earlier intense episodes. The ancient quasar era was different. It was a time when matter had not yet settled into the calmer structures seen nearby. That chaos could feed black holes rapidly, but it could also produce feedback strong enough to regulate them. A quasar shining fiercely can heat and expel gas, limiting its own growth. The black hole becomes both eater and interrupter, drawing in the fuel that allows it to shine while releasing the energy that may clear the fuel away. This balance links the growth of supermassive black holes with the growth of galaxies themselves. Observations show that central black holes and host galaxies often carry related histories, though the exact cause of those correlations remains complex. A galaxy provides the reservoir and gravitational setting for the black hole. The black hole, during active phases, sends radiation, winds, and sometimes jets back into the galaxy. Over time, the two evolve together, not as equal objects in size, but as connected systems sharing gas, motion, and energy. The largest ancient quasars therefore ask more than one question. They ask how black holes grow, but also how the first galaxies assembled enough material at their centers, how gas cooled without fragmenting too much, how radiation changed the feeding flow, and how cosmic structure became organized quickly enough to produce such engines. Every distant quasar is both a beacon and a clock. Its light announces a feeding black hole, while its distance measures how little cosmic time had passed when that feeding was underway. The most extreme cases make the clock feel tight. They do not necessarily break the standard picture of cosmic growth, but they press it toward its most efficient possibilities. They suggest that nature sometimes found fast routes to collapse, feeding, and assembly under early conditions that are hard to reproduce in the present universe. As telescopes look deeper, especially in infrared light that can reach through cosmic expansion and dust, the population of early black holes is becoming less like a set of isolated curiosities and more like a developing map. Some new candidates may reveal smaller seeds, others may show active black holes in faint young galaxies. Some will be revised as measurements improve. This is part of the caution required. Mass estimates for distant quasars depend on models of gas motion, luminosity, line widths, and assumptions about geometry. They are powerful tools, but not perfect ones. Even so, the pattern remains meaningful. Supermassive black holes were present early. Some were already immense, and their growth was entangled with the first major structures of the universe. The strange physics of black holes therefore expands from the horizon to cosmic history. The same object that traps light locally can reveal the timeline of galaxy formation when it feeds. The same darkness that hides an interior can make a young galaxy visible across nearly the whole observable universe. Giant ancient black holes are not only monsters of mass, they are constraints written in light, telling astronomy that the early universe learned to build deep gravitational centers with surprising speed. What remains uncertain is whether those centers began as the deaths of the first stars, as direct collapses of vast gas clouds, as repeated mergers, or as some combination still hidden among faint galaxies not yet fully seen. The horizon is small, but the question around it has the size of cosmic dawn. A white hole begins as the time-reversed shadow of a black hole, where a black hole allows entry but forbids escape. A white hole would allow escape but forbid entry. Matter and light could emerge from it, yet nothing from the outside could cross inward through its horizon. The idea sounds at first like an invention made to balance the darkness with an opposite brightness, but its origin is more disciplined than that. It appears inside the mathematical extensions of general relativity, in the same broad family of solutions that made black holes thinkable before astronomy made them visible. In the simplest eternal black hole geometry, the equations do not describe only the outside universe and the black hole interior. When the solution is extended as far as the mathematics allows, another region appears, one that resembles a black hole running backward in time, along with additional space-time regions disconnected from the ordinary outside world. This does not mean nature must build the full diagram. The real universe is not required to realize every part of an ideal solution. A collapsing star creates a black hole with a history, not an eternal object that has always existed. Still, the appearance of white holes in the mathematics matters because it shows that extreme curvature has more possible shapes than the familiar one-way horizon. A white hole is not known to exist. No telescope has confirmed one. No astronomical object has been securely identified as a region that matter can leave but never enter. The reason is partly physical. A white hole would likely be unstable. The surrounding universe contains radiation, dust, gas, and gravitational disturbances. If nothing can enter a white hole, then even a small amount of incoming matter piling near its boundary may disrupt the ideal structure. In a universe as active as ours, an object that requires such perfect conditions may not survive, or may never form through ordinary processes. Black holes arise naturally from collapse. White holes do not have an equally clear birth channel in classical astrophysics. They are therefore less like hidden stars waiting to be catalogued, and more like open questions about what the equations permit when pushed beyond the conditions that formed them. Their scientific value lies not in evidence already gathered, but in the way they expose the incompleteness of the story. If a black hole forms, evaporates, and eventually reaches a quantum regime where general relativity can no longer be trusted alone, then perhaps the final state is not simple disappearance. Some approaches to quantum gravity suggest a black hole might tunnel into a white hole-like configuration, releasing information that had been hidden for ages. Such ideas remain speculative, but they aim at a real problem. They ask how the universe keeps its quantum accounting when horizons appear to hide details too well. Wormholes enter from another branch of the same geometric imagination. A wormhole is a connection between separate regions of space-time, a tunnel-like structure in the equations that can link distant places, different universes, or distinct regions of a larger mathematical diagram. The word tunnel is useful but dangerous. It can make the structure sound like a carved passage through an existing wall, with travelers moving through a dark tube from one opening to another. In general relativity, the wormhole is not inside space in that simple sense. It is a shape of space-time itself, a geometry in which two distant mouths may be joined by a shorter internal route. The earliest versions connected black hole and white hole regions in idealized solutions, but they were not traversable in the practical sense. They would pinch off too quickly, or place the traveller behind horizons from which return to the original universe would be impossible. A mathematical connection is not the same as a usable bridge. The distinction is essential because black hole physics often permits structures that are coherent on paper, but fragile in reality. The equations can describe a path. The universe can deny the conditions needed to walk it. Traversable wormholes would require even more unusual ingredients. To hold a wormhole open, ordinary gravity is not enough. Matter and energy as normally observed tend to focus space-time inward, encouraging collapse rather than keeping a throat open. A stable traversable wormhole would likely need exotic negative energy conditions, a form of stress and energy unlike ordinary matter. Quantum effects can produce small negative energy densities in restricted settings, but not in the free and abundant way a large wormhole would require. This does not make the idea meaningless. It makes it constrained. Wormholes are valuable because they test the edges of relativity, quantum field theory, causality, and energy conditions. They ask whether space-time can be arranged into shortcuts without producing contradictions, and whether quantum theory allows enough unusual structure to support such arrangements. In many cases, the answer appears to be no, or not in any form useful for travel. Yet even negative results teach something. They show how strongly the universe protects causality, how difficult it is to keep horizons from forming, and how closely geometry is tied to the physical character of energy. Spinning black holes add another layer of temptation. In the ideal Kerr geometry, the singularity is not a simple point but a ring, and the internal mathematical structure can include paths that seem to lead into other regions. Some diagrams suggest passages through inner horizons, white hole exits, or repeated universes stacked in an intricate pattern. The images are fascinating because they turn the black hole interior into something more elaborate than a final crush. But the realism is uncertain. Inner horizons may be unstable. Tiny disturbances falling into the hole can be amplified enormously, producing a violent effect that may destroy the smooth passage the ideal solution seems to offer. Quantum gravity may remove or transform the singularity. The ring structure may signal not a gateway, but the failure of classical theory under conditions it was never built to complete. This is a recurring theme. The most dramatic possibilities often arise exactly where the confidence of the theory is weakest. General relativity points toward them, but it also warns that near singularities, curvature grows beyond the regime where a smooth classical spacetime can be the whole answer. The same caution applies to the idea that black holes might create new universes. Some speculative models propose that what appears from the outside as collapse could, from another side, resemble expansion. A black hole interior might connect to a new region of spacetime, perhaps even a baby universe, separated forever from the parent universe by the horizon. Other models imagine the Big Bang itself not as a beginning from nothing, but as a bounce from an earlier contracting phase, with white hole-like features in the deep past. These ideas are not established descriptions of reality. They are attempts to understand what replaces singularities when quantum gravity is included. The motivation is serious because singularities mark the breakdown of known equations. A theory that predicts its own failure has pointed to missing physics. Black holes and the Big Bang are the clearest places where that missing physics becomes unavoidable. Whether the answer involves bounces, remnants, white holes, holographic descriptions, or something not yet imagined remains open. The speculation is permitted only because the known facts have led to a boundary. Past that boundary, humility becomes part of the method. Information recovery may be the strongest thread tying these possibilities together. If black holes evaporate through Hawking radiation, the detailed information about what fell in must either come out, remain in some remnant, pass into another region, or force a revision of quantum theory. Many physicists expect the information is not destroyed, but exactly how it is preserved remains one of the most subtle questions in theoretical physics. White hole remnants offer one possible picture, where the black hole's long-hidden contents eventually reappear through a future outward-flowing phase. Holographic ideas offer another, where the information was never truly lost inside in the naive way, but encoded at the boundary and gradually returned in correlations within the radiation. Wormhole-related ideas have also re-entered modern theory in a more abstract form, connecting entanglement, geometry, and information in ways that do not resemble ordinary tunnels for travel. The old science fiction image of a shortcut through space is only a surface reflection of a deeper question whether connections in quantum information and connections in space-time geometry are two expressions of the same underlying structure. The strange physics of black holes therefore ends not with a simple answer, but with a narrowing of uncertainty. The well-established picture is already extraordinary. Massive stars collapse, horizons form, time and space curve until escape paths close, quantum fields make darkness faintly warm, accretion disks and jets turn the regions outside horizons into engines bright enough to shape galaxies, supermassive black holes grow through cosmic history and challenge models of the early universe. Beyond that secure ground, white holes and wormholes stand as careful speculations, not proven objects, but mathematical possibilities that reveal whether known theories are incomplete. They should not be treated as promises of escape or shortcuts waiting just beyond present engineering. They're better understood as questions given geometry what lies on the far side of collapse, what replaces the singularity, where information goes, and whether space-time itself is more deeply connected than it appears. The black hole began as the most final object in the universe, a place defined by no return. Slowly, under the pressure of relativity, quantum theory, and cosmic observation, it has become something more subtle, a boundary where endings, hidden records, and possible beginnings are difficult to separate. In the end, the black hole remains less like a single answer than a place where many answers meet and begin to change shape. It begins in the life of a star, in heat, pressure, fuel, and collapse. But it does not stay only in stellar astronomy. It becomes a question about time, about whether a clock is ever separate from the path it takes through spacetime. It becomes a question about emptiness, because even the quiet vacuum around a horizon cannot remain entirely without consequence. It becomes a question about information, because whatever falls inward seems hidden too well for quantum theory to ignore. Around it, matter may shine, spiral, and sometimes escape in narrow jets before the final boundary is crossed. Far beyond it, galaxies grow, gas cools or fails to cool, and ancient quasars carry the record of horizons that became enormous when the universe was still young. The black hole does not need to reveal its interior to reshape the imagination. Its power is partly in what it withholds, a surface without substance, a darkness with a temperature, a simple object with only a few public traits, and a surrounding universe made brighter by the difficulty of falling in. White holes, wormholes, and deeper theories may or may not survive as descriptions of nature, but their presence in the mathematics shows how far the question reaches. The strangest physics is not only that black holes trap light, it is that they force the laws of nature to speak to one another at their limits, where gravity, quantum fields, time, heat, and information can no longer be kept apart. For now, the horizon remains quiet, the universe continues around it. Matter circles, light bends, and the hidden center keeps its silence, leaving science with a boundary that is not empty, not solved, and not finished.